recording device initiated. Here it goes. What do I need? Okay, so today's topic, the existence of the derivative. And when does the derivative, well, let's put it this way, when does the derivative not exist? We talked about this yesterday. Can you give me an example? Ethan. A cusp. Now, we didn't use that word yesterday. We used a different word yesterday. Corner. There's a difference. All right? Here's a corner. Where the derivative is defined on this side, and it's defined on that side, but it's not defined here. That's a corner. This is a cusp. Imagine that the derivative is getting steeper and steeper and steeper, and eventually it's vertical here. I didn't draw it too good. Let me draw it better good. Hang on. Yeah. That was, the idea is it's like almost vertical. It's basically vertical there. Something like that, right? So if the derivative is not defined on one or the other side or both, that's a cusp, okay? Corner. Corner. Cusp. And of course, where the function is discontinuous, the derivative is not defined either, because remember, differentiability implies continuity, and the contrapositive. What's the contrapositive? The function is not continuous at that point, it's not differentiable at that point, right? So if the function has a removable discontinuity, like this, no, wow, this is getting bad today. Like this, maybe, oh God. Right, a removable discontinuity, you can fill in the hole maybe. It's discontinuous there, so it's not differentiable there. And if you have, that's also known as a point discontinuity. And if you have an asymptotic discontinuity, something like this, we have a vertical asymptote. The problem here is that the derivative doesn't exist. Remember, the derivative is a limit, and the limit, if it exists, is a number. That's not a number. If I have vertical slope, that's no slope, that's, I guess you could call that infinite, right? Infinity here, negative infinity there, and so forth, okay? All right, since you know everything about differentiability and continuity, it's time for some free response practice questions. Take a look at 81 AB5. Some of the AB questions are repeated on the BC exam. This is one of them. This was a BC 2. Uh-oh. We're actually seeing some BC questions. Oh my gosh. And tomorrow you're going to see some more for the pre-test. And Friday you're going to see some more for the test. All right, just so you know. The pre-test is 2 free response questions, and the test is 2 free response questions. And guess what? This is 2 free response questions on this sheet. Alrighty, so 81 AB5. Let's see how we can tackle this thing. It says that f be a function defined by a piecewise. Okay, let's make a piecewise defined function. Okay, so f. This is 81 AB5. There's also BC2 that year. The piecewise defined function goes like this. It's linear, mx plus b stuff, when x is less than or equal to 2. And it's parabolic elsewhere. But we don't know this constant k. Okay? So when x is bigger than 2, you have this line. When x is less than 2, you have this parabola. Part A. For what value of k will this function be continuous at x equals 2? Notice this is a polynomial. It's continuous and differentiable everywhere. This is a polynomial. It's differentiable and continuous everywhere. The only problem is in a piecewise defined function, you might have some kind of discontinuity or something here. Right? So what value of k will make it continuous at 2, where it breaks? Can you make the line touch the parabola at x equals 2? For different values of k, it may not. For infinitely many values of k, it won't. There's one value of k which will work. How do you find it? Say what? Yes, but no. Got to be more detailed. Remember the definition of continuity. You're all honorary Cubans. What is it? How does it go? Patrick, you know? What do you do first? Okay, got to find the limit at 2. Okay. It boils down to what you said, but let's be more precise. You got to find the limit at 2. What else? Well, we said what equal to each other? The two sides have to be the same, so the limit has to exist. Okay. Yep. That's one step. There are 3 steps. I. Remember, I told you, honorary Cubans. I can nominate you thus since I'm dual nationality. All right, so, you forgot definition continuity. The function must exist or must be defined at 2. The limit must exist at 2, and they have to be the same thing, right? All right, so let's go through it. Is there an f of 2? If so, what is it? Well, which branch involves 2? The first one, because it's an equal to here and not equal to here, right? So technically it's here. So I go 2 times 2 plus 1. He's plugging in 2. Is 5. Okay, that was tough. Now what? Who's next? Let's see some hands out here, guys. Just talking to me. Okay, and since it's different function on the left and different function on the right for x equals 2, you got to do it separately. So let's show that the limit on the left, as h approaches 0 from the left, is the same as the limit on the right. If the limit isn't, if these two limits are not the same, the limit doesn't exist, and forget it. It can't be continuous. Now be careful. We're trying to approach 2 for the point of tangency, right? But h is delta x, how far away the secant point is from the tangent line point, right? If I'm trying to get a tangent point here and approximate it with a secant line here, right? I'm trying to move this point up. That's h. As h goes to 0, we end up at the x value that we want. All right, so there you go. So let's do this guy on the left, 2x plus 1. And let's do this guy on the right, 1/2 x squared plus k. All right. So, well, I mean, is this a weird limit? I'm sorry, what am I saying? I'm going crazy. I'm thinking ahead. Wait, I'm sorry. I was thinking of the derivative. Wait, I'm going crazy. Yeah, that's what you were saying? Yeah, we want the limit at 2, so we're taking the limit as we approach 2 from the left and 2 from the right. I'm thinking of head to part B or something. All right, thanks. Sorry. I got a little crazy. All right, so anyway, is this a plug-in limit for 2? It's a plug-in limit for anything. It's continuous and differentiable everywhere. By the way, you already did it. What is it? 5. What happens if we plug in 2 over here, though? You get 2 plus k, right? Because 2 squared is 4 over 2 is 2. So k has to be 3. Ta-da! Okay. That tells you what k is. Now, what do you have to say? The function has to exist there. The limit has to exist there. If k is 3, the limit is 5. Say so. Say that f of 2 equals the limit as x approaches 2. And by the way, what is it? It's 5. Right? So you forced the issue. If k is 3, the limit is 5, the function is 5, you're done. Okay? So, when you're dealing with continuity, you have to do these 3 steps. It might fail here, it might fail here, it might fail here. You have to be very detailed. Okay? K approaches 2? X approach, that's an X, so yeah, sorry, that's a weird X. Okay. Alright, so that was part A. Any problems on part A? That's it. All that writing. I'm done. Yeah, well, if you want to play it safe, you might write a little sentence. Yeah, it's all there. And there's nothing much to say. The function exists there, the limit exists there, they match. Boom, done. I mean, what more are you going to say in words? It's right there. Okay, B. Using this value of k equals to 3, A, determine whether f is differentiable at x equals 2 using the definition of the derivative to justify your answer. Okay, part B. Well, let me go to the next page. Part B says, apply f prime equals what? What's the general definition of the derivative now? The limit as h approaches 0 of what quotient? F of x plus h minus f of x over h. Now this is where I got crazy. I was thinking on the left, we're talking about this function. So as h approaches 0 from the left, I'm going to use f is 2x plus 1, right? And on the right of 0, h is positive. As h approaches from the right, h is getting smaller and smaller from the right. I'm going to use the other function, which is now 1 half x squared plus 3. We're going to use the 3. Okay? So, what's the limit? As h approaches 0 from the left, is it the same as the limit as h approaches 0 from the right of the difference quotient? Now, I'm going to apply it to f is 2x plus 1. So what do you write? 2 times x plus h plus 1. That quantity minus what? 2x plus 1, the function itself. Okay. So we're going to try and work this out. And hopefully it's the same as this side, so we can prove differentiability. Now remember, maybe continuous step but not differentiable could be like a corner. Right? Okay, it's not a cusp, because the derivative on the left comes from the line. It's n. The derivative on the right is from a parabola. It's got to be defined. So it might be a corner. All right. So what function am I plugging in on this side? 1 half x squared plus 3 that we got down here, remember? Where it said use your value for k. All right, so it's 1 half what? X plus h squared plus 3. That quantity minus 1 half x squared plus 3 itself, the function. Okay? Be careful with parentheses and stuff, because remember when you subtract, you add the opposite of everybody. Careful. All right. So what is this limit? Well, you know how to simplify stuff like this. It's not a plug-in limit, right? It's over 0, we plug in 0. So it's not a plug-in limit. How do you simplify it? Maybe we can fix it. What would you do? Distribute the 2? Okay, so you get 2x plus 2h plus 1. How about we distribute the negative? In other words, add the opposite. What are you adding? Negative 2 and negative 1. Okay. All right, let me just focus on this side for a moment. So, anything interesting going on? What about the 2x? Go away. What about the 1? Go away, and you get 2h over h. And what happens with the h's? Goodbye. Didn't do the limit yet, though. What's the limit as h goes to 0 of the constant 2? Well, it's a constant, so it's 2. Okay, that was 2. But you knew that because it's a line. And this has mx plus b. The slope is 2 everywhere, right? It had to be. All right, but we're just showing it using the definition, like this said. Okay, let's do the same thing over here. What are you going to do with this? Throw that out, right? So x squared plus 2xh plus h squared. Now it's over 2, right? Okay, divided by 2. Divided by 2. I'm breaking my own rule. I'm doing 2 steps in 1. Divided by 2. Okay? I just distributed the 1 half over that. Don't forget the plus 3. And then what am I really adding? Negative x squared over 2 and I'm subtracting 3, so I'm adding a negative 3. Okay? I want to change everything to adding because I don't know how to subtract. Right? We don't know how to subtract. We know how to add the opposite. We don't know how to divide. We know how to multiply with the reciprocal. All right, anything interesting going on here? What about x squared over 2? So at least the baby, right? And what about the 3's? Oh, yeah, yeah. And the 3's are gone, right? Okay. xh plus h squared over 2, is that it on top? Okay, over h, I'd be back. All right, this stayed. And limit, as h goes to 0 from the right, what happens to the h's now? Common factor, so I can cancel it out and get x plus h over 2. Okay. So what's that limit? As h goes to 0, you just get x. But we're interested in what x value? At x equals 2, therefore, at x equals 2, the derivative exists. That's shorthand for exists. That's shorthand for exists. Alright, so therefore absolute derivative exists because x is 2. Okay, good. So it is differentiable when k is 3. Fine. So it's continuous and it's differentiable. So it's not a corner, it's not a cusp, nothing weird. Alright, remember differentiability implies continuity, so if we prove differentiability to begin with, we already got continuity, but that would be hard to do that ahead of time. And then what about part C? Maybe I'll go over here. Part C. It says let k equal 4. Alright, so now f of x equals 2x plus 1 when x is less than or equal to 2, and it's x squared over 2 plus 4 when x is greater than 2. And it says determine whether f is differentiable at 2. Just for your answer. Is f differentiable at 2 if k is not 3? K is not 3, right? Why is that important? You know what I mean? It's not continuous. And what do we know? If the function is not continuous, then it's not differentiable. Write that in words. I'm shorthand. Okay, that's it, done. It's only continuous when k is 3. So when k is 4, it's not continuous at x equals 2, so it can't be differentiable at x equals 2. You write that verbiage, write a sentence. Don't write what I wrote. I'm trying to save a little time in class. All right, so just write that out in words. At x equals 2, the function is continuous only when k is 3. Therefore, the function is not continuous at x equals 2 means it's not differentiable at x equals 2. Say something like that. Something in English will do. All righty? Any questions on 81 AB5? That was supposed to be a tough AB question. They get tougher. AB1, AB2, AB3, AB4, AB5, AB6. I think it only went up to 6 that year. Sometimes they go to 7. Right? 6 was like the toughest AB question, right? So this was supposed to be tough. It's just basic definitions of differentiation and continuity. This we should know like the back of our hand. All right. Any questions about that? Any problems? Anyone? Anything? Yeah, Ethan.
Threes cancel out.
Oh, where? Show me where I did. Let's see. I'm going to back up. The continuity part here.
No.
The derivatives.
Yeah.
Over here. Okay. What part are you talking about?
Because when you FOIL that, it just ends up being plus 3 and then minus 3.
Yeah, they cancel.
So if it's 4, it would be plus
Well,
4 minus 4.
Yeah, but the point is, you would. Well, no, that's not the point.
So you could differentiate because, like you have the same derivative.
You might have the same derivative, but it's not continuous there. They don't touch.
It's not the same.
Yeah, it's like a point discontinuity. Oh yeah, we skipped that. There's there's corner and cusp, there's undefined, and there's, it's like it jumps or something. Yeah, that's what that is. So when k equals 4, it's a line. It's a line on one side and a parabola on the other side, but they don't touch. Right. So I just missed that one. A jump discontinuity. Okay. Yeah. Good point. All right. But that's why it's discontinuous. To forget it's not differentiable. Why? Because look how many tangent lines I could draw here, any which way I want. Infinitely many tangent lines I could draw touching here. Okay. All right. Take a look at the back of the sheet. We're on 76 AB7. Oh God, this is supposed to be tough. They don't do AB7s anymore because they're just too tough. Oh God. And by the way, it's a BC6. It's pretty tough too. Oh, are we ready for this? How many days of school already? Oh God. All right. 76 AB7. Says, for a differentiable function f, let f star be the function defined by, let's see, f star, not f prime, derivative, f star, a different kind of derivative. The limit is h approaches 0, that sounds familiar, of f of x plus h, that sounds familiar, minus f of x minus h, oh well, all over h. I'll give you a hint. How lies about differentiability. How will give you derivatives at corners and cusps, or corners, okay? Because how uses this definition. That's another derivative. It's called the symmetric difference quotient. Why does how use that? Because it converges faster for smaller h's. I think h is hardwired at 20,000 or something, okay? So how will use this, but since it's approaching h from the right and, approaching x from the right and from the left, the derivative may exist at a point where you have a corner according to this definition. So remember, just because Hal says so doesn't make it so. You got to know what you're doing before you ask Hal anything, okay? He's evil, don't trust him as far as you can spit at him. All right, yeah, Ethan? I'm saying this is the definition of the derivative using the symmetric difference quotient. They're giving you something different. All right, can you find f star for x squared plus x? Okay. All right, so if f of x is x squared plus x, can you find an f star for it? All right, well, just do the same kind of thing we usually do. It's slightly different definition, but so what? Okay, so it's going to be a limit as h approaches 0 of, what do you write for f of x plus h? Yes. And I can't read that name. Somebody long? Mitchell? Mitchell, right? Yeah, right. Is that you? I can't read that. No? Looks like Aaron. I guess so, okay. Thanks. Yeah, looking for Mitchell?
I'm still there.
He's still there. He never leaves. Okay, anyway, so what am I writing? Quantity x plus h squared plus x plus h. Okay, good. That's this part. When I plug in x plus h, where I see x, it's a composition of this function with x plus h. This stuff minus what?
X plus h squared.
Okay. I'm plugging in x minus h on both, right? All over h. Okay. There's a lot of foiling going on. Oh, God. Well, let's see. Limit as h goes to 0 of x squared plus 2xh plus h squared plus x plus h. Did I do that right? Okay, quantity minus x squared minus 2xh plus h squared plus x minus h. Is that right? Sure, whatever.
Wait, no.
No?
Honestly,
I know, why?
minus x plus h.
Why? Why? What? I didn't do that yet. There's a plus here. This is the function. This is the x squared plus x. This is the x squared plus x. I'm subtracting, right? F of x plus h minus f of x minus h. This is part of the function. All right, don't get crazy. I know, you're confused because you're usually subtracting f of x and that's it, but... All right. Well, let's see. X squared minus x squared. Goodbye. Terminator, right. 2xh minus a negative 2xh? Oh, yeah. Okay, so 4xh. Remember, how do you subtract? You never do. You add the opposite. So it's 2xh plus 2xh is 4xh. Okay. H squared minus h squared. Goodbye. X minus x. Goodbye. H minus negative h. Plus 2 h's. Now this is over h, and you still got to do the limit. And what happens to the h's? Hasta la vista, baby. Right? And, okay, fine. Anyway, yeah, and there's no h's left. Right? That's weird. Okay, so what's the limit of this? Since there's no h's, it's got to be, it's independent of h. It's not changing. H, it doesn't matter. Now, what do you notice? Yeah. Which 2h? It's not over 2h. The question has h here. I said for a second, that is a valid definition of the derivative, if you had a 2 there. What they're giving you is not a valid definition of the derivative. That was my point of putting the 2 there, but I got rid of it. Okay? So the 2's not there. So anyway, what's the derivative supposed to be? 2x plus 1. What did you get? 4x plus 2. So guess, what's wrong with this derivative? It's missing the 2. I told you about. Remember the 2? It's off by a factor of 2. Divided by 2, what do you get? What do you get? 4x plus 2 divided by 2? Is 2x plus 1. Duh. Oh boy, come on. They think we're that silly? We know this stuff. It's off by a factor of 2. It's 2 times too big. Because the definition derivative should have a 2 there. Right? You didn't know that, but now you do. Okay. All right, now it says do the same thing in part B for cosine. And just show again that you're getting twice what you should get. What's the derivative of the cosine supposed to be? Negative the sine. So what do you think it's going to be in this case? Negative 2 times the sine. Well, I think it's off by a factor of 2 bigger. Yeah. All right, so let's do part B. Let's do f star on f is cosine. Okay, so I'm going to say f star is the limit, as h approaches to 0, of, remember, it's f of x plus h minus f of x minus h over h, right? So cosine, what am I writing? X plus h, now what? Minus cosine x minus h all over h. Now if I gave you this on a test like on Friday, I would give you the identity that expands cosine of alpha plus beta. But we used it the other day, do you remember? Cosine, minus sine. That's where the negative sign comes from, the minus sine. All right, so I'm going to write it that way. I'm going to say the limit, as h goes to 0, of the cosine of x times the cosine of h minus the sine of x times the sine of h, quantity minus, do the same here, cosine of x times the sine of negative h. Be careful, that's a negative h I'm plugging in, right? Minus the sine of x times the cosine of negative h. I messed up. I'm thinking the sine. Whoops, I messed up. I'm messing up things. Stop it. It's cosine minus sine, right? So give me a pen. Okay, that's not good. Okay. Cosine minus sine. Thank you. That was a bad boo-boo. All right. Well, I don't know if that helps much, but realize that you know the cosine of negative h equals what? That's a trig identity you should know. Remember we said in the unit circle, I can't draw on this thing, all right? If this is theta and this is r, let's say r is 1. If this is theta and this is r, this is the cosine of theta, this is the sine of theta. Okay? But what if you put in a negative theta? In other words, the angle doesn't go this way, it goes that way. So it looks like this. Well, this x value is still cosine theta. And this y value is this flipped over, so it's how big? What's y here? If y is sine theta here, it's negative sine here. What does that tell you? When you plug in negative h, cosine of negative h, it's just cosine of h. If you plug in sine of negative h, it's negative sine of h. So this becomes negative, and this becomes positive. Okay? All right, so maybe could I just fix it here? This is basically the same as cosine h. And this is the same as sine of h if you change the SIGN. Don't confuse the SINEs with the SIGNs. Alrighty. And now, we do stuff. Well, let's see. What happens? Cosine x, cosine h, minus cosine x, cosine h. What happens? Goodbye. Negative sine sine x, sine h, minus sine x, sine h. And it's a negative 2, right? That's where the negative comes from. All right, I'm going to get rid of this. So we get limit, as h goes to 0, of, let's see, negative 2 sine x, sine h. And don't forget, it's still over h. And you know this limit, we've done this a gazillion times. It's 1. So, did we not get twice what we should have gotten for the derivative of the cosine? Okay, so at C, write an expression that expresses the relationship between the function f star and f prime, which denotes the usual derivative of f. Well, let's see. F star is equal to, how's it related to f prime? So what should I write? 2f prime. Done. That's it. Alrighty. So, yes? Wait, I can't hear you. What?
It would have been the same, so let's say f prime equals f star, for example.
Yeah, same thing, yeah. I wrote it that way because we ended up with an extra 2 in front all the time, but it's the same thing, yeah. Maybe, I don't know, they might get a little pesky on the AP, might want to say it this way. F prime of x is equal to 2f, f star of x equals 2f prime of x, right? Function notation, they get a little pesky about that. You want to write, what did you write? F prime of x is f star over 2? Yeah, either way, one or the other, that's fine.
Why is the negative cosine negative? I don't understand why it just turned it positive.
Where?
Sine. Positive.
Where are you?
That. Up.
Up.
That was for when it was.
I'm plugging in negative h. The cosine of negative h, the cosine of negative, let me think, 30, all right, the cosine of 30 is a half. The cosine of negative 30 is also a half. That's all I'm saying.
Also the same thing.
Yeah, because it's the same, because the cosine is the x value on the unit circle. So if you're in the first quadrant or if you're in the fourth quadrant, the x value is the same. What's going to change is the y values.
So that this is on.
So if you plug in, if you have sine of negative h, that's the same thing as negative sine of h. This used to have a negative here, right? I just changed it. This became positive because I'm multiplying by a negative sine h. So here I'm multiplying by positive cosine h, nothing changed. And here negative sine h, I changed this sign, which was negative, right? So this is from the trig identity, cosine minus sine. That's how you get the negative sign, the minus sine. That's why it gets negative. The derivative of the cosine is negative, but the derivative of the sine is not. Right? You've noticed that, yes? Okay, so I'm going to save it here.